So we will now talk about Abbe's theory for coherent imaging. So Ernst Abbe was a giant of microscopy. He was not only a really amazing physicist who really for the first time properly understood how microscopes behave and how to use maths to describe their performance, but he was also a really good person. He became, in fact, the founder of the Carl Zeiss Foundation. Of course, Zeiss is still one of the major manufacturers of microscopes to this day, and the Carl Zeiss Foundation exists to this day. And he was an interesting man, also because he was one of the first bosses really to run a company which looked after the employees really well. So welfare was at his heart, and he was amazing all the way around. But today I will talk about Abbe's theory of coherent imaging, and the diagram you see here on the presentation slide shows you how this essentially works. So we have our standard 4F imaging system, we have our object plane here, and we have the Fourier plane and the imaging plane, objective and tube lens. And I want you to imagine you have a transparent object in the object plane that has a certain modulation on it. Let's suppose you have a transparent grating, like the one I showed you the other day. I showed you, I projected through a slide a laser beam, and you saw the two diffraction orders appearing, and that told you, of course, that the modulation on the slide, it performs a modulation of the amplitude that is a sine wave, right? So that gives you the two orders at e to the I k naught x and e to the minus I k naught x, and that's the sine modulation. And there was a zero order as well, because the whole thing is shifted. There's a DC component in the field. So let's suppose we have such an object. So here it's just a rectangular grating, and then the light gets diffracted from this grating, and then we get the spectrum of the field distribution here, which mimics what the grating is doing. And the spectral components here are then synthesized, they're put together by the tube lens to synthesize the image. And so the first thing I want you to notice that if, let's say, the grating has a period d, then we get diffraction orders that appear at different angles theta. And just to recap that with you, I will go to the paper briefly and show how we derive these angles for the maxima. We've seen something like that already for Young's slit experiment, but just for a grating that is illuminated by a plane wave, like so. Let's suppose I have a plane wave coming from left to right, as usual, has wavelength lambda. It impinges on a grating, and I'm just drawing one period here. So this is D. Then each one of these openings here will emit spherical waves that will interfere. And then I have my tube lens as my objective, as usual. Here's my objective. And the objective is in the back focal plane of the objective. We have the Fourier plane. So let me draw that here. So what we get is that because this adheres to Fraunhofer conditions, parallel rays are bundled to the same point, and the phases are preserved. And so let's just take the two rays that go straight ahead behind the aperture. They are obviously focused to the center, to a point P like that. And of course the waves, because this is a coherent imaging situation, this wave and that wave are going to be completely in phase, and therefore you get a bright spot here, and the field is a maximum, and when you square that field, it would be constructively interfering, and you get a bright spot. Okay. Now, at what other angles do you get bright spots from this? So if we look at this again, so if I draw this down here, so here is again the spacing D. Now let's look at, if I draw this reference line like that, and I draw two rays that go off, let's say one in this direction, another one in this direction, so they're parallel, so these two would be imaged to the same spot by the objective lens, as we know. Then their phase difference is given by this path difference down here. It is given by this path difference here, and this path difference is given by d sine theta, where theta is this angle here. And when do you get maxima? Well, you get maxima when that path difference, d sine theta, is equal to m times lambda, where m is the order. M can be 0, 1, -1, 2, -2, and so on. So it's an integral multiple of a wavelength. So just to draw this, so if I have a wave like that here, then these waves will be exactly in phase. So you need to have that exactly be a lambda here. I didn't draw this very well for this to work, right? And so then you get, for this angle theta, then this may focus to this point here, and that may be m equals 1, and then here m equals 0, that's the central order, and that's m equals -1, and so on, right? So you will get another angle further up where you get further maxima, all right? And so when I look at this now, if I go back now to my electronic presentation, then what you see on this slide here is precisely this situation. We have m times lambda is d sine theta for the maxima, and so for m equals 0 we go straight forward, and we will image to a point here in the Fourier plane. So m equals 0 is just the frequency corresponding to the DC component. You recognize that now, right? And then for the first order, you will get again two bright spots for m equals 1 and m equals -1. So here we go. Now you can in fact think of this. You can think of this as waves traveling off in different directions from this grating here, and the waves have spatial frequencies, and the spatial frequencies are k0, k-1, k+1, and these frequencies appear in the Fourier plane as k+1, k0, and k-1. And if you look at this, k0 is, if you just take that component here on its own, this component will be synthesized by the lens into a plane wave. So actually, the k0 component here of the input field will yield a k0 component of the output field. So this is essentially the plane wave background that you get from this situation. Now let's look at something else. Let's look at these two components. Let's look at frequencies k+1, k-1. These two will travel back, and they'll be imaged and interfere on the image plane, because it's coherent, these two fields will interfere with one another and they will produce a standing wave, and this standing wave has a frequency that is given by e to the ik naught x plus e to the minus ik naught x, so it gives you a sine wave. And here comes now the genius of Abbe, and I want to go back to the paper now, because you can think, of course, of the object. The object is a grating function. Let's look at the grating function here. Let's plot that. So if I plot the grating function, then it will look something like this. Let's suppose I have a grating that has this. This modulation. So it's essentially a top hat, a periodically spaced top hat profile. So essentially you can think of this function as a convolution of a series of delta functions with a rectangle function. Okay? So that's how we can describe a square wave. And let's just, so this would be perhaps, so the period of this would be d in this particular case. So we could, we can think of this, so this is in x, and this is the, let's say this is the field here in the object plane. All the phases are coherent because we're illuminating with plane, we're illuminating with plane waves. So just to say that again, so from here to here would be corresponding to one period of the grating. So here I make a modulation of the function that's a square wave, where the peaks and troughs are exactly the same width. Okay, and actually, what this is it's what you can see is that this has a DC component in it because it's shifted from 0, right? So we can represent this now with our knowledge of Fourier of Fourier theorems and Fourier synthesis. So we know then that this function has a DC component. So maybe a component like that, x, and there will also be a component that is like that. So there will be something that has, if I just make this slightly smaller so you can see more of the screen. I'm sorry. I could draw this as follows. So let me just do this just so I get the right pitch for this. So so there will be a component perhaps that looks like this for sure. Can you see this? Of course, this mimics already this function quite well. Now that's symmetric around 0 here, so we need that DC component as well. So it's this one here plus this one, and then actually there will be another component in there for this square wave that looks like this. Something like that. Perhaps, plus that, and so on. And so we found, in actual fact, we can synthesize these periodic functions with a series of periodic functions, orthogonal functions, as we've seen in the Fourier analysis lecture. And this is what Abbe actually saw, and it's ingenious and it is incredibly intuitive. So it actually, this picture that I like to give of the microscope as being the ultimate Fourier synthesis machine, Abbe's theory brings this out beautifully, and I will show you why. Because of course this original function here, this original function is given by the sum of ck e to the I kx, where k goes from minus infinity to infinity. And in fact, so you have, this would be here, this would be c naught, and k would be naught, right? So you just have a dc term. This one here would be c1 times e to the ix, so k equals 1. This here turns out to be c3 e to the i3x, so this has frequency 3. In fact, you only have odd harmonics in here, so it'd be k equals 1, k equals 3, k equals 5, and so on. And actually all the even ones, k equals 2, k equals 4, k equals 6, they drop out. As you will know, if you've done a Fourier transform of a square wave like this, okay? And so Abbe, if I go back now to my presentation, so Abbe realized that the function I have in the object space can be decomposed into its Fourier components like this. So here's the first harmonic of this. The first harmonic you can think of as a if you replace this grating here with just the first harmonic, all you end up with is two components going off at k plus 1, k minus, and giving you two frequencies, right? Plus k plus 1, k minus 1. They resynthesize and give you exactly that frequency back. Can you see that? And the next higher order, so this could be the 3 omega for a square wave function, or 3k for a square wave function, that goes off to the next order, so k equals 2. You can see this will give you 2 orders. And so you decompose the structure into its harmonic components. Each one gives you diffraction orders, and you resynthesize them, but here you see the problem. As soon as the frequencies get high, frequencies in the object that are very high, so this is already high frequency content that I need to faithfully recreate the square wave, these high frequencies will diffract the light out to angles that are extreme. And as soon as these angles are larger than what the objective lens can capture, we don't transmit information through the microscope anymore. And so, of course, the maximum angle is just given by the numerical aperture, right? So the 0 order is here, first order is there, second order is there. I mean, the minimum information you might need to say anything about this grating at all is you need to capture these first orders, because that's the first harmonic frequency that's in there. If you lose that, you don't even see any modulation intensity down there. So if you block those 2 orders here, you'll just get a DC light. If you want a bit more of a square wave here, you need to capture at least the second order as well. And of course, you want many more orders to see this. So it's beautiful, right? So each one of these orders here, you can also think of as, it's analogous. This interference here is analogous to the Young slit experiment we had earlier on, right? You have two slits, 2 spherical waves turning into plane waves. They interfere on the image plane, and they give you exactly the modulation back that you need. There are 2 things you should note. The first is that high spatial frequencies, they travel at large angles, and those spatial frequencies that cannot be captured by the lens, those will be lost, they will not appear in the image, and therefore the image is degraded. So you are, like in the Fourier synthesizer program, if you just drop out a few terms, the function that you synthesize will become less and less representative of what you wanted to get. Okay, so what is that maximum angle? So we know that the first order is m lambda d sine theta. So for d equals, so rearranging this, so for m equals 1, we get d equals lambda over sine theta. And sine theta here is the numerical aperture. That angle here turns out to be the numerical aperture, right? So you need to have the resolution you gain is given by precisely that formula. And of course, this is what we already know. We did this the other way previously. We derived this. But here you see now, this is Ernst Abbe. And he has on his gravestone this formula. It's a super important formula, and it holds to this day, despite some Nobel Prize winners, recent ones, trying to modify the formula and making it their own. That's a bit of a that is actually not correct. I should be very careful what I say here. I might get myself into political trouble. What I mean is that this formula holds for standard ways of imaging. You cannot separate points better than lambda over NA. Now you see two more factors. You see the factor 2 on his gravestone. In fact, where does the factor 2 come from? Well, that would be the incoherent PSF, right? So the detail is twice as large than what you get for the coherent PSF. And the reason for that, you know, because we square the coherent point spread function when we do that. So that's what this formula represents. And the n is the refractive index, which we did not take into account. But it then does turn out, I'll finish at this point here, with this part of the lecture, but it does turn out that actually for the coherent case, the smallest separation between 2 points that you can resolve is in fact really lambda over NA, or lambda over n sine alpha. And with that, you know everything about the microscope really, and we can now describe techniques, specialist techniques, microscope systems, and start using this in earnest and see modifications in the future that allow us to gain extra information and even to gain resolution using special tricks that are better than this important formula here. But that's not because the physics is wrong here, the physics is right. It is because you're exploiting other methods to generate contrast, not just interference of light waves. And with that, I finish this part, and I'll see you in the next lecture.